Thank you very much, Georgia, and thank you to all the organisers for the opportunity to come to this lovely island and take part in this school. So this is the title. Oh, thing is going to be a problem. Maybe I can do something with this. Let's get rid of that thing. Maybe this is going to work better. So this is the title I would have given had I been giving this lecture maybe 5 years ago. Multiscale materials modelling, connecting electronic and atomistic scales. I'll try to tell you a little bit about that, but since we are, in fact, in 2025, we need to say with machine learning in some way or another. And the particular variant of it that I will try to convince you is useful is what I'm calling scientific machine learning. You might ask what I mean by that. Has anyone heard the term scientific machine learning before being used? George, that doesn't count. Yeah. So what I mean by that is fusing bottom-up mechanistic models, things like density functional theory or molecular dynamics, with data that's coming down, rather than just a pure data-driven model, which is a big box that you throw data into and get something out. And this is an attempt to try and find the best of both worlds, where we use mechanistic models where we can, but we improve them and correct them with data where necessary. Okay. I also thought it might be useful to tell you where Warwick is, because not everybody will have heard of it, especially as slightly confusingly, the University of Warwick is not actually in the town or the city of Warwick. It's in a city called Coventry, which is roughly at the centroid of England, so about as far as you can possibly get from the sea in every direction. So that's why George and I are particularly enjoying being here this week. At Warwick, I helped to run a centre called HETSYS, the Centre for Doctoral Training in Modelling of Heterogeneous Systems, which has quite a lot of overlap with some of the topics that we're learning about this week at the school. And we try to train PhD students so that they're equipped for working in this interdisciplinary environment, with a particular focus on software engineering, so writing code that outlasts the PhD, so that you can contribute to packages and do things which have a longer lasting point. On scientific machine learning, which I've already told you a little bit about, and then also, as we'll see towards the end of the lecture today, on uncertainty quantification, which means trying to produce numbers that come out of your calculation that aren't just a point estimate, but a probability distribution, some sort of idea of the confidence that you have in the results that you're calculating. I think that's really important. It's something that our experimental colleagues have traditionally been much better at than we have in the modelling domain. I think it's something that we all need to try and do a little bit more about. We focus at different scales, quantum, atomistic, and continuum. What I'll show you today is really mainly at these scales, and we also have cross-cutting themes that we're expanding in terms of biomedical applications, not so relevant for this week. Development of new algorithms, so that's where we work with our colleagues in mathematics and computer science to try and actually come up with new approaches. And materials characterization, which is really overlapping well with what we're doing today. That's where we have joint PhD projects, where one student is doing theory and another student is doing experimental work, and they try and work closely together. And they're all very happy and jolly, as you can see in the photo. Okay, what do we do in my own research group? So here there's maybe not perfect alignment with energy materials. I've been working for a long time on what I call chemomechanical processes, but actually a lot of the methods are in common. So in today's lecture, I'll focus mainly on methods, which I hope will be broadly interesting. But what we try to do is try to understand processes that involve both chemical reactions, so breaking of chemical bonds, rearranging of chemical bonds. Something like fracture is ultimately driven forward by breaking bonds, but at the same time is driven by long-range stresses which are applied very far away from where the bond is breaking. So that's the combination of local chemistry and long-range mechanics that makes things challenging to model. Applications here include trying to make diamond drill bits which last longer or have better wear resistance, understanding friction, so this is an AFM tip, an atomic force microscope tip. We're rubbing that around on a surface, we're inevitably rearranging chemical bonds. At the same time, there are long-range stresses that need to be taken into account. Maybe a bit closer to an energy application, trying to extract metal ore from oxides. This uses something like 5 or 10% of total global human energy consumption, just crushing rocks into tiny pieces so that you can expose a little bit of metal and extract it. If we had a better understanding of the mechanical processes and the coupling that they have with chemistry, we could really substantially reduce the energy consumption of this process. And again, in the end, we're breaking things, so it's fracture, and it's a bond-breaking process down at the atomic scale. More recently, I've been based in an engineering department, so I've been trying to be useful and working a lot on metallic systems, so on understanding and controlling plasticity for turbine blades, but also for nuclear fission and fusion applications. So this is a reactor vessel. We need to put something really strong around the outside which can absorb the tremendous thermal flux that comes out of a future fusion reactor. And the only candidate really is tungsten, but unfortunately its mechanical properties aren't quite good enough. So we need to understand and control the mechanics a little bit better. Then there are many new steels which we would like to use in energy applications, so in wind turbines or in electric vehicles, but unfortunately they're vulnerable to chemical embrittlement. Hydrogen can get into steel and cause it to crack, when otherwise it should be plastic and should behave in a pleasant way. So these are just examples. More specifically, I want to tell you a little bit about some of the projects going on in the group, because I've chosen examples from these to illustrate the methods that we'll be looking at later in the talk. Lakshmi has just finished. Actually, I'm not going to be showing any of her work today. She worked on radiation damage in steels. Ian worked on uncertainty quantification for machine learning potentials. We'll come to that towards the end of the lecture. Matt is working on interactions between dislocations and impurities. So when you have a fusion reactor, you have hydrogen or helium being produced. That gets into the metal matrix and reacts. We need to understand and control it. Valdas is working on machine learning models one scale further down. Again, we'll see that later in the lecture. So trying to learn effective Hamiltonians rather than interatomic potentials. Tom is working on dislocations as well, but in ceramics, in semiconductors rather than metals. Fraser is working on fracture. We will see a little bit of that just as an example. Facundo is in the first year. He's just starting, working on dislocations and strength. And George, who is here with us, is also just starting this year and is working on development of what Ian did, really, trying to harness and control uncertainty and use it so that we can design things with targeted properties. So in the theme of materials discovery. Okay, so that's just the introduction. As I said, I've split this talk into parts. The first one has got no machine learning in, so we're going to just try and recap and revise a little bit some of the basics, taking into account that we've got quite a diverse range of backgrounds and students. If it's boring for you, then sorry, but I'll try to do it reasonably quick, and hopefully it will be interesting for most people. This is what I found when I came into my office one day a few years ago. So there was a big glass wall here that had shattered into 1 million pieces. So that's an example of the large-scale processes we want to understand, brittle fracture. If you zoom in, you find individual fractures, which, if you go down far enough, are mirror smooth and atomically sharp. I didn't actually do that with the fracture in my office, I'm afraid to say. But in principle, individual cracks are mirror smooth and super sharp. And you can see on a nanometer scale, it's completely flat. So if we want to understand that, we really need atomistic techniques. We need quantum mechanical accuracy in principle to describe bond-breaking processes. On the other hand, if we're looking at a metal, it's actually a lot more challenging. So if you elongate a metal, it fails through the accumulation and agglomeration of voids, which are much bigger, which are micron scale. That's really outside of the remit of what we can directly contribute to at the moment with atomistic modeling. We can maybe look at the initiation and the embrittlement of fracturing metals, but we can't really model these big messy processes, so effective models are needed. So this is the sort of traditional hierarchy of multiscale materials modeling approaches. We've heard already about density functional theory. There's actually a whole range of quantum chemical techniques further down, which are even higher in accuracy, but even more costly. I'll spend a little bit of time later on tight binding style models, because I think there's a lot of promise for those models. So that's where we have some sort of effective Hamiltonian, which traditionally was written down with pen and paper with some kind of table of matrix entries, where they were traditionally very hard to parameterize, very hard to find new ones for new systems. And I think that's somewhere where scientific machine learning can really help. So where we can learn a Hamiltonian or learn a density matrix, learn some kind of effective thing from DFT, which we can apply one scale further up. Then we have molecular dynamics using some sort of potential. We'll talk more about different choices for potentials, and then onwards and upwards to larger scales with corresponding decrease in accuracy. And the key things to note here, if we want to simulate long times or large systems, we can't directly use accurate methods. So the first idea for the kinds of processes that we want to look at in the research I talked to you about would be to use empirical interatomic potentials. Who has used an interatomic potential and done some MD at some point in their research so far? Okay, not everybody, so it is good that I included this slide. So for many people, this is very obvious, but I think it's worth emphasizing. You have to put in the interatomic potential somehow. You have to say how atoms interact with one another. That could be very simple. It could be something like a Lennard-Jones potential with a repulsive wall and some dispersion interaction like this, and then we add up all the contributions from all pairs of atoms and get a total potential energy, and then we can take a derivative of that. That gives us a force. We integrate, and we know how to move all the atoms. So we assume that the atoms themselves are classical particles. This is usually fine unless they're hydrogen, and if we have forces, we can move them. But we have to think how to do that. We need to do it on a timescale that is given by the speed at which things vibrate. So that's typically a femtosecond timescale, and we have to think how to pick the interatomic potential. So there are different things we could do. We could use quantum mechanics directly. We could use density functional theory. We could get the forces from that. That's accurate. It's called ab initio MD. It's very slow because every time we need to solve the quantum mechanical problem. We could use an empirical potential like this one, or of course over the decades, much more sophisticated potentials have been proposed. So we could just have springs, we could have Lennard-Jones, we could have something called an embedded atom model, which is widely used in metals. And we have to choose the parameters of that model. So in the Lennard-Jones, that's just the sigma, which is a length scale, and the epsilon, which is an energy scale. We have to decide how we're going to do that. There are basically two ways. We can either try and reproduce experimental quantities directly and choose effective parameters that do that, or we can try and match ab initio forces and energies and choose the potential parameters that do that in the best way. And that second idea is called force matching. It was initiated by Ercolesi and Adams in the early 90s, and that eventually led on to what has become the modern field of machine learning interatomic potentials, where we make a much more complicated version of this with many more parameters, typically hundreds or thousands, and we fit them to a representative database of configurations. And we'll look at that much more in the second half of the lecture. So just to mention that that is a possibility for now. Okay, there was something at the very end there that I missed. What was it? Okay, there are codes. You shouldn't write your own MD code. Probably everybody knows that. Okay, so what happens if we try and apply one of these potentials from the 80s or the 90s that have been crafted with love and involve a mixture of art and science in order to produce them to a problem like this fracture problem? So we know from continuum mechanics that as you go close to a crack, it's a mathematical singularity, so we have a divergence of the stress. The stress shoots up super fast. The real material is discrete. It can't go to infinity. It has discrete atomic sites, and so it goes up at a slightly different rate, a little bit softer, and actually the stress concentration is captured really well. So this is an example of somewhere where maybe you don't really need a complicated atomistic model. Anywhere outside of here, everything is matching well, but in here, if I look at the dynamics, things go completely wrong with a simple potential because it's not sophisticated enough to break chemical bonds. You tend to overestimate how hard you need to pull. You put in far too much energy, and you get a big mess here. We're getting emission of dislocations, plasticity, the crack is arresting. It doesn't look like what we see in an experiment, where it's completely flat and completely smooth. So this is an example of somewhere where traditional interatomic potentials are not really sufficient. We could look at another example. This is a superalloy. So a superalloy is a single crystal turbine blade that you would find in an aircraft. It's maybe about this big, and it's grown very carefully in controlled conditions, so all the atoms are perfectly lined up. It's an FCC matrix. It's a little bit more complicated because it has precipitates inside. So it's basically nickel, but it has hard lumps inside, which are nickel-free aluminium. These are the gamma prime phases, and dislocations tend to travel freely in the gamma phase, but they can't get into the gamma prime. So we're really interested in understanding the structure of dislocations. In an FCC material, dislocations dissociate into partials, so they're not just pure dislocations, they separate, and they have a stacking fault in between them. I'll explain why that is important when thinking about the potentials in a minute. But you can see we have these two halves, the dislocation here, they're moving around dynamically. And what we could maybe observe experimentally, we could take a thin slice of this material, we could put it into a TEM, transmission electron microscope, we could actually see the separation, and we could measure experimentally what this distance is. That's the kind of thing we could use to validate our approach. However, getting a quantity like that right relies on a really careful calibration of your model. We'll come back to that shortly. The other alternative that we could use is to directly try to simulate quantities of interest with density functional theory. We've seen some really great examples of that working well earlier on from Silvana, and I'll give one or two more examples. I don't need to spend too much time introducing DFT because Silvana covered that earlier on. Essentially, we have all the parts that we do know, and then we have a contribution that represents effects of exchange and correlation, which we don't know and for which we need to make approximations. So we put in all of the physics that we have, and then we have a part that describes the missing part. Unfortunately, we have to do that because we can't solve the full Schrödinger equation directly for realistic systems that contain more than a couple of electrons. So that's where DFT helps. It gives us this exchange correlation function that we put in where we model the electrons as non-interacting, and we instead incorporate an effective term to describe the interaction and the effects of exchange and correlation. So local density approximation, generalized gradient approximation, meta-GGA, etc. would be examples. Okay, and DFT I think has succeeded because you think that the scaling is quite expensive, order n cubed, but it's actually a good balance between accuracy and cost. So the quantum chemistry methods tend to be much more expensive. They maybe scale as the 5th or the 7th power of the number of atoms that you're interested in. And then empirical methods tend to be faster, but less predictive and less accurate. The real challenge is applying it to big systems because of this, and also to long time scales. And that's where, again, in the second half of the lecture, we'll look at how machine learning can use data from what we can compute here accurately and make effective surrogate models using it. Incidentally, what I'm showing you here is showing you that you get more than just energies and forces out of a density functional theory calculation. This is the charge density near to a tip of a crack in silicon as I'm pulling it apart. And you can see electrons leaving this bond. So if we wait for it to loop around again, we don't have to decide for ourselves what a cutoff is or when bonds are broken or not. Okay, so here is the bond, and then it's broken. You can really see you can observe that directly. We have access to the electron density, which is what I'm visualizing here. And that's not been fully exploited yet, I would say, in machine learning models. They tend to focus only on energies and forces so far. So I think there's going to be a second wave, and it's already coming, where we use more of the things that we have access to from the first principles methods. Okay, and there are standard codes. We've heard about some of them already, and so it's a well-established technique. So coming back to the applications that I'm interested in, there are some things that you can go and grab directly with single point density functional theory calculations where you don't need to do a very elaborate or complicated setup. And one of them is actually the fracture toughness. So that's how hard you have to pull a material in order for it to break. And the reason that you can estimate that reasonably clearly is that it's really driven by a long-term thermodynamic energy balance. So what happens when you create a crack is you make two new surfaces and you relieve strain or stress from some elastic energy from some region ahead. So there is this 100-year-old theory of fracture mechanics that tells you that it's favorable to propagate when the amount of elastic energy that you release exceeds the cost of creating two new surfaces. So in order to make a prediction about that, we need to do DFT calculations of surface energies and of elastic properties. This G here is a function of the elastic properties, which we can compute. So we did this a few years ago in collaboration with an experimental group at Imperial led by Finn Giuliani. They very, very carefully set up a piece of single crystal silicon carbide. They stuck a wedge in the top up here, an indenter, and they pushed very slowly and very carefully under a microscope. And the crack is growing very stably, so it's taking 400 seconds to move by a few millimeters. And if you look at the load that they had to apply, you have to do some calculations at the continuum scale to work out what that load is. And you compare the single crystal experiments with the direct density functional theory calculations, you get reasonably good agreement within 10% or so, in comparison to previous experiments which weren't done so carefully or weren't so well aligned. So if we're talking about thermodynamics, then DFT is fantastic. We can compute quantities, we can make predictions. But if we're interested in mechanisms or in kinetics, it's much more challenging, and that's where we, I think, really benefit from potentials. I promised I would return to this example of the superalloy. So we have these two guys here, these two partial dislocations jiggling around, and we wanted to understand whether we can get this stacking fault separation distance right. So that's the experimental quantity that we'd like to get access to in this case. This is quite challenging. We have to think about what we put in to the potential and what we get out. And I'm trying to use this as a general example of when you fit potentials, it really matters what you put in your training set, what you think, what you need to get right. So in this case, this is an FCC material, so we put in the FCC energy volume curve. We carefully make sure we get the energy right as we stretch the FCC material. We also put in information about the stacking fault, so the energy of taking half a crystal and sliding it on top of another one. And so we get that right as well. You can see the red and the blue. You may not be able to read the caption, but when red and blue line up well, that's good. The embedded atom model is matching the DFT. So these things were optimized for when building the model. This one, which is the HCP phase, the hexagonal close-packed phase, was not particularly thought to be important, so it wasn't included. Unfortunately, locally, if you look at the stacking fault, if you look at the atoms on the stacking fault, their local environment is much closer to HCP than it is to FCC. So this is an example of something you might not have thought of, but if you don't include it, you don't get this trade-off right, and you get a difference in the interaction, which you can't correct for in a simple embedded atom model where you only have a pair term in addition to the embedding term. So the electrons are actually doing very similar things in the FCC phase and the HCP phase. So the electron density contribution, which is one thing that goes into the model, is pretty much the same. The pairs need to do different things, and you can't fit a single simple pair function to represent these two different things. Once you've diagnosed that, once you've understood why your simulation is giving the wrong answer, you could go back and fix it, but it's hard to do that beforehand. You really need to dig in and do a post-mortem analysis of what's going wrong in this case. Okay, I think we'll go a little bit further and then we'll have a pause for questions. So once you've kind of seen that some things work at some scales and not so well at others, it's obviously tempting to try and come up with hierarchical information passing schemes where we compute some number here and we put that into a larger scale and so on and so on. And that's a theme that we'll return to. And that's almost always the best way to go about doing multiscale modeling. At least in the past, it wasn't always possible to do that. And sometimes you actually need to, couple things. I went one click too far. Couple things concurrently. So this is an approach I worked on for quite a few years. I think it's now fading away a little bit in importance, but I wanted to bring it up because it actually helps a lot with understanding the motivations for some of the things we'll see in the second half of the lecture. So you can imagine situations where you don't need uniform precision. You know, there's some part of your system where stuff is happening, bonds are breaking, things are rotating, stuff is going on, maybe a chemical reaction is taking place, a catalysis process, etc. Whereas the rest of the system, not so much is going on, and you could manage with lower accuracy. And this is what we applied, first of all, to fracture. So you can take a very large system now, you can describe it with an interatomic potential, and you only need to correct things locally near to the place where bond breaking is taking place. And that fixes the problems that I showed you earlier on with overestimating how much energy you needed to put in to break bonds. So now we describe all of these processes nicely. Those of you that have studied silicon surfaces may notice we get the correct 2x1 pi bonded reconstruction of the silicon surface. So chemical things come out naturally, providing density functional theory captures them well. We've still got a timescale problem because we're doing DFT at every time step in order to evaluate the forces on these blue atoms. I'll tell you a little bit about how that works to sort of help get across the strengths and limitations. Essentially, we do a DFT calculation on the atoms that we care about, shown in black, augmented by an additional region shown in light gray here, which is chosen to ensure that the forces on the atoms in the black region are accurate. So we're relying on locality of forces. And then we paste together two sets of forces, the inner ones and the outer ones. We have an overall vector of forces which are more or less correct. And we can converge by making this gray region wider. And in covalent materials, this works well. So you need 7 or 8 angstrom, and you get within a few % accuracy with your forces. In oxides, it's terrible, and really it doesn't work at all. Even if you try more advanced approaches, like embedding the DFT calculation itself in the electrostatic field that arises from charges and dipoles centered on atoms outside, it still doesn't help too much. So the red is cluster embedding, and the green is with the electrostatic embedding, but still you have to go to very long distances. So really this approach is not really viable in systems with long-range electrostatics. And those remain challenging for machine learning interatomic potentials for exactly the same reasons. Those rely on the same locality assumptions. Metals, again, it's much better because of physical screening processes, so 6 or 7 angstrom, and you have forces which are quite accurate, so the approach works well. You have to think where you need the high precision, and that's a choice of the user who's running these kind of calculations. So you have to have some criteria for saying, I trust my model here and I don't trust it there. And we'll come back to think about that when we talk about uncertainty towards the end of the lecture. If you have a model which could estimate its own uncertainty, this would be a great way of deciding where to use a more accurate model and where to use a less accurate one. What you would like, really, is that all the observables that you compute, all the derivatives of energies that you actually measure in experiments, to be localized as you take 2 atoms very far away from each other. And you can do that under certain conditions. There are maybe more rigorous ways of deciding where to place your high accuracy method. So we've worked on one relatively recently where you can define some kind of error metric on your overall system, and you can decide to optimize where to place high precision regions in order to trade off between cost and accuracy. Okay, so just coming back to the strengths and limitations of this approach. So we rely on locality of forces, as in fact we do when we make potentials. We get the forces right, and actually we can move the quantum region as we do so. That's because the embedding is based on forces. That makes it relatively straightforward to do that. We can add chemical complexity. So we can actually put in a molecule of oxygen. We can see it diffuse to a crack tip, spontaneously dissociate. It's burning one silicon-silicon bond at a load which would not be favorable for the crack to advance on its own. We're not pulling hard enough for it to be energetically favorable for the crack to move on. But if we place that oxygen there, it reacts with the strained bond at the crack tip. It dissociates, it absorbs, and we've burnt a bond and we move on by one. And that's all things that we can do within a DFT timescale. That's a reaction which itself takes place in a few picoseconds, so we can do it directly in DFT. But we have to wait ages for the next molecule to get there and so on. So it's not really possible to study the whole process with DFT like this. We're using pretty simplified simulation geometries. These things are narrow in the direction, in the plane, into the screen. That's just to keep the cost under control. I can afford a few hundred atoms at DFT level, not more. And actually, one real challenge when I was doing this a few years ago is every time you move to a new system, you need a new embedding potential for the outside. It takes you ages to set that up. So this is, again, somewhere where machine learning can really help, because if we have already a good quantum mechanical description of some region here, we can fit a model to that and very quickly get an embedding potential. Okay, one more example, and then we'll have a chance for a few questions. So this is an example for nanotube polymer composites. What we're interested in here is the so-called pull-out force. We put some nanotube inside a polymer matrix, and we want to be able to make it strong so it resists pulling out. And here we used a slightly different criteria for doing the embedding. So this, my things always click on a bit more than I expect. This is very local, and so everywhere where there is a point of contact between a polymer molecule and the nanotube, we see a kind of increase in the local energy, the strain energy. So we can actually use the local potential energy as a way of measuring where we are unlikely to trust our classical model, and we can augment locally with lots of little separate spots of quantum mechanical accuracy. This was done using type binding, so it was a relatively cheap quantum mechanical model. We could place it in lots of places simultaneously. And you can validate this at a high level by looking at something like the stress-strain curve. So we apply a strain, and we see how hard we have to pull before the thing breaks. The full calculation can be done as a one-off in orange, and the very much cheaper QMMM-style calculation in blue gives pretty much the same failure strain. Whereas if you use only the classical model, similar to the brittle fracture examples that I showed you, you end up pulling much, much harder before any bonds break, because those classical models are not really designed for fracturing or breaking covalent bonds. Okay, so let's think about what we've seen so far and what the challenges are. We haven't really talked about timescale. And in energy materials, we're often interested in activated processes, in catalysis, in things that take a very long time, so in rare events. We need to think about how to access them. We're also often interested in larger scale processes. So we need to get information out of simulations that we do at this scale and up to larger scales. This is an example I wanted to show because it was done by a colleague who was at King's together with Giorgia and I a long time ago, Chiara Gattinoni, showing interaction between more than one defect. So now we have a crack here and a dislocation, both treated with higher precision. And we see when we start the simulation, it's predictive in the sense that we don't tell anything what to do. We don't tell the crack where to go. So it's pulled down by elastic attraction towards the core of the dislocation. It's going to take a little wobble and come down. This is a partial dislocation, again, like the ones I showed in FCC. So there's a stacking fault here, a weak interface within the material. So the crack takes a bit of a detour up the stacking fault. It's easier for it to propagate in that direction. And then after a while, there's too much shear. It's not favorable anymore, so it returns to the original cleavage direction. So these are expensive simulations because every step is involving quantum mechanics. But if you do a few of them, the idea is you can make a representative model at larger scale. So a very simple continuum model, for example, where you look around and you measure elastic energy, and it's informed by simulations that you've done here. This is roughly the same setup as the one that we just saw, where we traveled for a bit along the stacking fault. So these kinds of ideas allow you to access mesoscale or coarse grain scale and feed into engineering problems using atomistic input, where you could never get there directly by running the simulation. Okay, I think I had jumped slightly ahead and already started talking about rare events. And now I'm really ready to do that. So a reminder of what we're doing here. We've got quantum forces in some parts of our system, classical forces elsewhere. We'd like to be able to do things like calculate energy barriers. Usually you need access to a total energy in order to do that. We don't have a total energy. We've only got forces. So we're mixing together classical forces and quantum forces. We've got an overall vector of forces. We can control the accuracy of those forces by making our buffer region bigger so that our quantum forces are more accurate. So we're quite confident in these forces, but they're not the derivative of anything. And that sometimes upsets people when I'm presenting this method. However, we can use the so-called principle of virtual work to integrate the work done by those forces when moving along a path. And this actually works really well. So we can look at a direct energy calculation in comparison to what we get using only a very, very small quantum region centered on a moving vacancy in aluminium, and we get a good agreement. So we can compute barriers. That means we can feed in to kinetic Monte Carlo or larger scale models in this way. Here's another example of a dislocation in molybdenum. And again, here you can really see how we can converge this barrier with respect to the buffer width, so that layer of padding that we place around the quantum region. It's really expensive to do so, but if we make the calculation, that quantum region more and more well padded, the barrier does settle down and we get 0.1 electron volts. So we can compute energy barriers in really big systems with really complicated things going on. And you can see they're massively different than what you get, for example, with an empirical potential in this case. So I think this is quite a good example. It shows that it can be dangerous to rely on interatomic potentials outside of the domain of where they have been calibrated. And even if these calculations are expensive, it's useful to be able to do them occasionally to validate and to provide information. Okay, this is where I was going to mention coupling up to larger timescales. So once you've done this kind of thing, if you can extract barriers, you can extract energy barriers, so rates of processes, then you can parameterize a kinetic Monte Carlo model. You could do it using a potential, or if you're concerned about the accuracy of the potential, you might be able to do it directly with DFT, although these kind of calculations that you have to do in order to compute barriers, these nudged elastic band calculations, are quite expensive and quite hard to do. So maybe this is something to keep in mind for the second part of the talk, that we'd like to be able to compute these kind of things without directly doing the DFT calculations. Okay, if I've remembered right, this is the end of part one, so let me just summarize a bit. So quantum mechanics is very accurate in many material systems. DFT is a really good balance between cost and accuracy, but it still is limited. We can maybe do 1,000 atoms and a few picoseconds, but not much more than that. Classical potentials, really hard to make transferable. I didn't really emphasize the chemical species side of things, but I would say you can fit a good embedded atom model in a metal for maybe 2 chemical species, but not really more than that. So if you want an alloy with 5 or 6 components, it's extremely hard to do. Multiscale techniques such as QMM still have some value, I think. We'll talk about how they fit into the modern machine learning world in the second part, where you need localized high precision. So you know that your model is good enough in most of the system, but there are a few spots where you might need higher accuracy. And they can be extended to calculate transition rates if you know what your individual rare events are and that you'd like to be able to calculate. Then you can feed into kinetic Multiscale, and you can inform larger scale materials models. So I showed a continuum model. That could be a phase field model just as well. Is that the last point? No, okay. And there are clear opportunities to connect things I've been talking about in this first half with machine learning, which is what we'll do in the second half. But before we do that, let's have a quick break and see if anybody wants to ask anything about the historical part of the talk. Yes?
Question. I presume you, when it comes to the DFT simulations, do you perform them at 0 Kelvin, or are you able to perform them at higher temperature?
So do you mean ionic temperature or electronic temperature?
Well, I don't know.
Yeah, but no, both of them are not 0, I guess, is the right answer. But let me try and explain a bit more. So we're doing a molecular dynamics calculation. The atoms are moving around with the forces that we've taken by mixing together the DFT forces and the classical forces. So they're away from equilibrium. We take that snapshot, and we put it into DFT and evaluate it as a single point calculation. We're not doing dynamics in DFT at all. We're just getting energies and forces from DFT. But the atoms are displaced as they would be at finite temperature.
Okay.
Separately from that, we also have some smearing, which means that we're treating the electrons as not being at 0 temperature. That's somewhat artificial. It's to make the convergence of the DFT easier, and typically the amount of smearing that you use is rather higher than the true temperature. So often you would use maybe 300 Kelvin for your simulation if you want to do room temperature, but your smearing would correspond maybe to more like 1,000 Kelvin, so that you don't need quite such a dense sampling of the Brillouin zone with your K-points. So that's maybe more detail than you wanted. But
Thank you so much.
Yeah. Yes?
I think I understand how do you deal with the region like between the QM and MM, like because in one part you have like electrons, information from the electrons, and the other one you lose it.
Yes. So the common information is forces. Forces always live on atoms. They're local quantities, both in the quantum picture and in the classical picture. So we can just literally stitch together a combined vector of forces where we have quantum forces on quantum atoms, classical forces on classical atoms. We do one slight refinement on that to make sure we conserve momentum, which is to ensure that the forces sum to 0. So you can take the total force divided by the number of atoms and subtract it. That's a small correction. And then you have Newton's third law back again. But you don't have energy conservation because those forces are not the derivative of anything. But that's really it. So the way in which the padding is done ensures that every force that you are using is an accurate force. And then you don't need any other interface terms. There are other ways of doing QMMM that are used, for example, in biological systems where you have an energy mixing stream rather than a force mixing scheme. There you would define a quantum energy, a classical energy, and then you need a link term which parameterizes the interaction. The problem with that is that you have to somehow optimize that link term. That's usually done by saying that you know what the equilibrium geometry is. That's okay. You fix the parameters of that interaction based on the geometry, but it means that finite temperature observables aren't always as well characterized. Yep.
Well, yeah, you wrote atomistic simulation can inform like phase field and this thing.
Yes.
It's kind of informing. Is it in form of properties calculated fitting to phase field, or some parameters calculated, or is there any kind of other than calculating properties that we can inform phase field or any other kind of method?
Yep.
Can we like develop something phase field model totally from DFT because?
Yep, no, it's a good question. So phase field is a good example here because there is no true scale in the phase field model. So it's perfectly possible to bring the phase field right down to the atomic scale or to the quantum mechanical scale, and then directly to fit the free energy term that you use in a phase field model to effective observations from the atomistic model. You can't quite directly fit to the energies and forces because you want to include entropic effects, which will no longer be there once you have your phase field model. But you could fit to the results of dynamical simulations at the atomic scale. This hasn't been fully exploited, I would say. I think it's an important area that more work could be done in. There's something called phase field crystal, which goes in this direction. It includes the effects of anisotropy and so on, but it hasn't been as fully exploited as another example is DDD, discrete dislocation dynamics, and there are some works now that directly do MD calculations and use them to inform the mobility law for the dislocations that at the larger scale. Yep.
So you stitch together classical forces
Yep.
and quantum mechanical forces to get the most accurate vector you
Yep.
can get break it when the forces exceed some threshold, I guess. But when the bonds will break, do you know that from experiments or some empirical knowledge, or can you know that directly from the forces? And
Yep, no, it comes directly from the simulation. You don't have to put in any threshold or anything into the simulation. You're applying loading in some prescribed way, and you see in your trajectory the observations, which you can then compare to experiment. So you don't put any experimental information into the calculations that I've shown you at all. That's important to clarify.
Okay, so the bonds, they just break at some point?
Yes, exactly. So you have this vector of forces,
Yeah.
and you use that to do molecular dynamics in just the same way that you would do ab initio molecular dynamics or classical molecular dynamics. At every time step, given a set of atomic positions, you can calculate all the forces on all the atoms, and then you can use them with Verlet to move the atoms a little bit, and so on. And you can continue.
Okay, so when a bond breaks,
Yeah.
it's not because the forces exceed it?
No, it just happens.
Okay.
Yeah.
So it's just that the electrons, so it's more favorable for the electrons to go elsewhere
Yes.
and sit in that electron
Exactly.
bond?
Exactly.
Okay.
Which software do you use to actually combine this quantum and classical?
So this is really simple, actually. So it's implemented in ASE, the Atomic Simulation Environment. There's a Force QMMM class that I wrote that is in there. We have our own code as well, but if you just want to try it out, that's what I would suggest. You can also do it directly in LAMPS. There is a fixed hybrid that you can use to combine two different methods. Our code is called QUIP, Quantum Mechanics and Interatomic Potentials. It is still available. I'm not. It's the code that Alessio was talking about that he wrote in 2005. That's enough. Okay, anything else? I should probably keep going or we don't get through everything. What time did I start? 10:50. So,
We finish at 12:20.
okay, so we're about halfway. We have more.
10 minutes.
Yeah. So, part 2, scientific machine learning and how it impacts on what we've seen in part 1. So really the main focus of this part is jumping from the DFT scale to the empirical MD scale using machine learning interatomic potentials. There are lots of different ways to do this. The ones that I'm familiar with, because I've been involved in them, are the Gaussian approximation potential gap, the atomic cluster expansion ACE, which was originally developed by Ralph Drautz in Bochum and has been widely applied, and then the message passing variant of that, MACE, not to be confused with this cost action, which is a completely independent MACE. So those are the ones I'll be talking about, but most of what I'll say is general, and if you're using a different machine learning potential framework, then that's fine. Which one will we be using this afternoon, actually?
Just a bit of high level on it.
Okay, perfect. So I'll mention a tiny bit about that as well. Yeah. Okay, so the basic idea is that you somehow come up with some database of representative configurations. Actually, the best advice I would give anybody who's wanting to use these is not to fixate too much on getting that right first time, but rather to rely on this feedback loop I'll talk about in a minute, to iteratively develop this database. So you put some things in, you make a model, you try and do something with it, it will inevitably blow up in some way. Take some of those configurations where it's blowing up, evaluate them with DFT, add them to this database, and go around again. Exactly how you do that doesn't really matter. There are lots of recipes, but the key thing is to do that in some way, and then you converge, typically in a few iterations. So you have a database, you'd like to describe that. It's in high dimensions, so it's really hard because of the curse of dimensionality that tells you that the number of data points that you need to fill space grows exponentially with the dimension, so you don't directly fit it in that three-dimensional space. Instead, you fit it in some representative descriptor space, which is typically lower dimensional. This is at least the classical picture that applies to ACE and GAP, and also to the Baylor-Parinello neural networks, not so much to the graph neural networks, which discover their own descriptor as part of the training process, but it's still a good picture to have. So you have your high-dimensional space, you compute with DFT, energies, forces, and stresses everywhere in that space, and then you learn the mapping from atomic environments to local energies, and you add up those local energies, and you get a total energy. And you do it in such a way that it's the derivatives are analytic, so you can also get forces out of the model. Okay, so this is probably a really key slide, so I'm also going to pause here to see if anybody wants to ask anything about the basic philosophy before we get into the details. Probably. So that is the thing which is method specific. So I will explain that in a minute for 2 particular methods, but there are other choices as well. The idea is, so if you're sitting on an atom, you have a cutoff, maybe 6 angstrom. The total number of atoms in your neighborhood is maybe 200, and each of them, no, maybe 100. Each of them can move in 3-dimensional space, so that's 300 degrees of freedom. You can't fill that 300 degree of freedom space with calculations. It's just too big. So instead, you find some lower dimensional representation of that space. That's the general idea. We'll talk about the specifics in a minute. Yep.
But here you just have the DFT calculations and then the fit of the
Yes.
So you don't have any experimental data.
Correct. Yeah. So that's why I said it's really in the spirit of this Ercolesi-Adams 1994 force matching idea, rather than mixing together some things that come up and some things that come down. Yeah. Okay, so specifics. It relies on the locality of site energies, so that's why those locality of force plots that I showed you earlier on are relevant. Yeah, local energies and forces are not exactly the same thing, but there's a connection between them. So in materials where there's either screening that's significant or where interactions really are short range, this works really well. It's not a solved problem in electrostatically dominated materials, I would say. There is a lot of work being done, but it's not in the same state. The SOAP gap approach, as a descriptor, actually uses something called SOAP, so the smooth overlap of atomic positions. And the way that works is that you sit on an atom, you find your neighbors. On each neighbor, you place a little Gaussian, and this gives you a density field. And you can add up all of those small Gaussians, you have a density. You then need to find a way to compare that density with another density in a way that gives you rotational invariance. This is the tricky part. So if I take my system and I turn it upside down, its energy doesn't change. And so my model should include that symmetry automatically. This is what SOAP does for you. It analytically computes the integral of one density smeared with another density and integrated over rotations. I haven't written the formula down, but you can find it in this paper, for example. And this kernel here compares the environment in which we'd like to make a prediction, EI, that's the energy we'd like to predict. This is its environment with a set of representative configurations, RS, and then there's a coefficient that we learn when we fit the model that tells us how much each representative environment contributes to predicting the energy. So you can view it as Gaussian process regression, if you're familiar with that, or kernel ridge regression, if you're familiar with that. We have a kernel in here, which is where all the nonlinearity goes, but these alphas are actually just a linear model. So it's really easy to fit. It's a convex optimization problem. There's a formula to get the alpha, essentially. You don't have to optimize via gradient descent like you do with a neural network. It's also important to mention this M here is a user parameter. In the GAP framework, we call this the number of sparse points or inducing points. It doesn't have to equal all of your data set. So typically you might have 100,000, 200,000 atomic environments in your DFT database, but this sum doesn't have to go over that many points. It might be 1,000 or 2,000 or 10,000. It's something you choose. So you're effectively defining how big your basis needs to be in order to represent the variations that you see across your data set. The atomic cluster expansion ACE is actually simpler, especially in its linear setting. So the idea here is local energies come just from a linear combination of basis functions. And the way that this works is that these basis functions already include all the required symmetries. So these are invariant basis functions. They've already been integrated over rotations, essentially. And it's really nice because it's mathematically complete. So that means if you were to go to an infinite body order, it would form a bijection between the original space and the descriptor space. And so you'd be able to go into descriptor space and back again without losing any information. In practice, you don't do that because you truncate at some body order, 2-body, 3-body, 4-body. So it's not a bijection, but you need that if you're going to actually reduce the number of descriptors that you have in comparison to your original dimensionality. Okay, so it's a recipe that gives you invariant basis functions. That's the sort of level of detail that I want to go into. I think we might hear more about some of these concepts later on. And that gives you a way to predict local energies. These coefficients, again, you obtain from a linear fit, so from least squares. Really, really easy. You evaluate these basis functions on all of your data points, and then you do a least squares fit, and you have a model which can give you local energies. You add them up, and you get total energies. ACE is about 10 to 100 times faster than GAP. So if you're starting now with this, that would be a really good starting point. The reason that it's faster is you don't have to do all this kernel comparison business. It's just a linear model. And we've shown relatively recently that it's almost as accurate, or just as accurate. So this is for silicon, a comparison of point defects, elastic properties, surface energies, large range of quantities, and they're all within about 5% of DFT. So this was based on a data set that we developed specifically for doing this with the GAP model. We just took that same data set and refit it with this new ACE model, and we get comparable accuracy. And I can now revisit the simulation I showed you earlier on with silicon, and I don't need quantum mechanics anymore to describe the bond breaking. So this simulation, the bonds snap in just the right way. We also get the surface reconstruction coming out. So for this example, we don't need to do this quantum mechanics, molecular mechanics anymore. We can really do this directly with a machine learning interatomic potential. This looks a bit jerkier than the simulation I showed you earlier. That's just because this particular simulation is quasi-static. So I'm pulling and relaxing and then pulling and then relaxing. I could have done a dynamical simulation, and it would have looked more similar to what we saw earlier on. Okay, I think maybe I'll do one more slide, and then we can again see if there's any questions. So the reason this is fun and exciting, and I think this is a really great time to be in this field, is we can now do stuff that we could never do before. I can now run a simulation where I'm looking at cracks running really fast for really long times, rather than the small simulations that I showed you earlier on that were limited by the DFT timescales. So Fraser in his PhD is looking at dynamic fracture. That's when cracks are running at a significant fraction of the speed of sound in the material. What we're doing here is we're sitting in the reference frame of a crack that's actually zipping through a piece of diamond at 5,000 kilometers per second, and we're adding material on the front as the crack moves forward. We're chopping it off the back so that overall we're in equilibrium. So the thing is zipping along through, and that was just not possible with a quantum mechanically accurate model until this year or last year. So we can start to really look at details of bond breaking processes and how they impact on large-scale phenomena. So I'd say the answer to the first question, for systems where this assumption is valid, is now yes, and there are lots of things we can do. There are ways that we can combine with ideas from QMM. I'll talk about them shortly, and then I'll talk about foundation models and fine-tuning, and then I'll talk about uncertainty, and then we'll be allowed lunch. So before I go on to those application-focused things, are there any questions about the ideas or the implementation, what I've shown? Yes?
You have the input for the Z direction. If we see here the XY direction, do you consider that it is periodic?
Yes. So in these simulations, it's periodic and it's quite narrow, 1 or 2 lattice units. I'll show an example later on where, given the potentials, we can now go large in that third direction as well. With DFT, it was not possible to do anything other than this 2.5-dimensional simulation. But with potentials, we can make it large in the third direction as well.
Is this model realistic?
It's realistic because above the critical load, cracks, the barriers are all 0. So all the bonds do break more or less at the same time. And the crack front advances as a battalion rather than as an individual soldier. But it depends on the specific setup whether that's valid or not. If you were looking at an impurity, that would be a problem because you'd have an array of impurities that were very close to one another. That might not be physically reasonable. So. Yep.
Short light question. You use periodic boundary conditions.
Yes.
How to say you have some stresses in the whole box, and
so it's periodic in the Z direction. It's got open boundaries at the top and at the two sides, so that you can apply the stress. That's right. And
applying uniformly in the whole.
Yes. Yeah. This is the so-called thin strip geometry, which has a mathematical solution, so we know in the continuum problem what we would expect, and then we can see how the atomistic solution differs from it. If you're only interested in the onset of fracture, it's better to use a different geometry where you apply a displacement field that you get from continuum mechanics on the boundary. So it depends, the details depend on the problem, but yeah. Yes?
How do you initiate the crack?
We put a big notch in, so
Yeah,
we're
you
not,
just put the notch and
yeah,
then you
then relax.
play and then it will propagate.
Yeah. So we're not studying the nucleation problem, which you could do, but you have to do it very slowly. I don't think I have a movie, but if you take a perfect crystal and you pull, you will initiate voids in there at some point. But on the simulation timescales that we can access, your strain rate would be much too high, orders of magnitude too high compared to experiments. So that's a harder problem. We need rare events for that. So we'll come back to that one. Okay, good. So I want to show a few connections between the two halves of the talk. One is this idea of high and low precision. You can do just the same thing with machine learning potentials. And that turns out to be useful because these potentials are quite expensive, especially the accurate ones like I just showed. And so we can use exactly the idea we had with DFT and with potentials, but instead with two potentials. So we have some region where we need high accuracy, we have cheap atoms, we have expensive atoms, and we mix the two together exactly in this way. Now we're doing a bit more carefully, we're doing blending between the two, because the cost of this high accuracy potential is a lot less than the cost of DFT. So we can afford to do this blending more gradually over a longer region. Okay, and Fraser is working on this. So we did it, for example, for diffusion of a helium impurity in tungsten. So we have a big box of tungsten. Mostly the tungsten is just flopping around in a harmonic regime. It doesn't need a very accurate model to describe it, but the interactions between the helium and the tungsten can't be captured by a simple model. So here for the expensive potential, we used an ACE, similar to the ones I just showed you for the fracture case. And for the cheap potential, we used something called UF3 from Matthias Rupp and Richard Hennig, which is really a generalized 2+ free body potential. So it's like a Stillinger-Weber or one of those potentials, but you machine learn the two-body part and the free body part. And so it's super fast. It's not very flexible, but it's fine for the bulk. And if we are careful about how we do this so that we match properties between the two regions, say, for example, we can strain so that we match the elastic constants between the two potentials quite well. Then if we look at observables like the diffusion constant for the helium moving around in the lattice with the full model and with the mixed model, then we get some very good agreement. And in this case, we get a big speed up because we're only paying for the high accuracy model where we need it, not everywhere. So I think this was a useful message from all the laboring with QMMM, that you don't necessarily need to take this fantastically good machine learning potential and just apply it uniformly everywhere. And then you can do fun stuff like this. You can put lots of helium in, and you can treat each helium as an impurity and treat it with the accurate model. So you could start to look at clustering effects and so on. Similar things that we could do with QMMM, but just on a different scale. Okay, I want to try and bring things together a little bit. So we've talked about passing information from DFT to potentials in order to fit surrogate models. We've also talked about simultaneous coupling. I want to show you a way of using the two in unison. And this example relates to the application I talked about earlier on of plasma-facing materials in future nuclear fusion reactors, where we really need to understand how to improve the mechanical properties of the tungsten, particularly when hydrogen and helium comes out of the reactor and gets into the tungsten. And traditional interatomic potentials don't describe the core structure of dislocations correctly. If you haven't seen these figures before, this is a BCC crystal. Red, green, and blue are 3 layers in the BCC, first red, then green, then blue. And then the arrows are showing the difference in displacements in the in-plane direction, out-of-plane direction. So it's a screw dislocation, which means all the displacement is out of the plane. And you can't really see anything if you visualize it directly. So instead, this arrow here is telling us what the difference in the Z displacement of the green and the blue guy is. So it's a very compact way to show the displacement field out of the plane. And what you can see really is that this one is wrong. It doesn't have good symmetry. It should look more like this, where you have a nice compact core and then everything lines up well. And this is what you get with either a very good embedded atom potential from Cosmin Marinica in CEA or a machine learning potential. And you don't actually need to treat very much of the system with an accurate model in order to fix that asymmetry that you're getting from the simplified model. So this is a good example, but it comes back to the question about 2D versus 3D. So when we did this a few years ago, we looked at the effects of hydrogen and helium on dislocation glide barriers in these narrow 2D cells, and we saw something that we thought was interesting, but we weren't really sure if it was meaningful. We'll come back to that a bit later on. But what we could do is use these quasi-two-dimensional structures to update the machine learning potential that we're using for the outside, for the embedding part, so that it knows how to correctly describe migration of dislocations. This is work done by Petr Grigorev, who some of you may know has just started a permanent CNRS position in Lyon. He was a postdoc with me and then with Tom Swinburne in Marseille, and is now just starting his own activities. So what Petr did was to use these ideas that I showed you on calculating energy differences by integrating forces. We do that in this QMMM style setup, and we know then what the reference results should be, so what the energy barrier, it's called the Peierls barrier. You apply a stress and dislocations move, but it's just an energy barrier which you compute with NEB. We know what it should be, and we have our original potential which doesn't get it quite right. We update the potential a little bit, so as well as describing the bulk material, it can describe this particular process. And the motivation for doing this is that then we can do this 3D business. So our potential is now good enough that we can make a big 3D system. The dislocation is described well there. And we only treat, for example, an impurity with quantum mechanics. So we need a small spherical region with a helium in it. We don't need a ginormous sausage treated with high precision method. And this is something that Petr has been working on for a few different applications. So this is the one I had in mind. If you put things in 2D, then effectively if you put a defect in, you don't have one defect, you have a big stack of defects. And that's not really the relevant regime if you have only a low concentration of helium. You would first have one helium somewhere, you wouldn't have a big line of them. So the fact that you see a change in the dislocation structure here is interesting, but maybe isn't the full story. If instead you're able to do this long dislocation core, which is now described fine by the machine learning potential, it's just the impurity part, which wasn't accurately described. We do that with quantum mechanics still. You see what you might expect, that far away from the impurity, the dislocation stays pretty much as it was before, and locally it transforms to a different kind of environment. So this was what we saw in the bulk material, the upward pointing triangle, easy core. This is the downward pointing hard core configuration, and it goes to something a bit in between. It's called the split core configuration. And we see a local change. So this is nice. What's even maybe nicer is that a new student, or a student Matt, who's in the final year with me, built a bit further on this and took an existing database for tungsten, for machine learning potential for tungsten, added in some of these configurations of helium interacting with dislocations, and was able to reproduce the same result that we got quite expensively with the QMMM, just with a potential. So once you know what you're looking for, which configurations to add, then it's possible to put all these things into databases, which you can then refit models, and you get the same results. But I think this was still valuable as a tool for discovery, for being able to do this. So I'm not quite ready to kill QMMM completely yet. Okay, I think 20 minutes, is that what we're? Yeah. So I'm just thinking what to, we'll stick with the fine tuning. We may not cover all the uncertainty. So the next thing is about foundation models. How many of you have come across universal machine learning potentials or foundation models already? Okay, not so many, so it's important that I explain properly. So this is a recent trend in the last couple of years, using the ideas that I've shown you in the last 20 minutes or so, but not just building a database yourself with your own configurations that you evaluate, taking in a giant database along the lines of what Silvana showed us earlier on, the Alexandria data set, or these kinds of things, materials project, and trying to fit a model that is supposed to be good for the whole periodic table or for a large fraction of the periodic table. And this is an extremely challenging thing to do. I, at least, was very skeptical. I didn't think it would ever work. I didn't think it would ever be useful, but I've been proved wrong. So I was one of the 50 co-authors on this preprint that you can have a look at with more details, which took the MACE model. So MACE is a graph neural network where the messages that are passed between one node to another are ACE features. So the atomic cluster expansion that we talked about just now, you take those things and you put them into a neural network. It's a message passing neural network. That means it has a bit further reach than just the cutoff of the ACE descriptor itself. You do 2 hops, essentially, where you pass information from a site to its neighbor and then to the neighbor of the neighbor. So rather than having an effective cutoff of 6 or 7 angstrom, you have a cutoff of 12 or 13 angstrom. And that, it turns out, is just about enough that it works okay for systems in which there's a bit of charge transfer or a bit of long-range electrostatics. It works surprisingly well, given that there is no direct treatment of the Coulomb interaction. It's really just the same ideas that we've seen now, but a bit longer range. Okay, so it's a graph neural network. It was initially trained on the MP-Traj dataset, so that's 1.5 million configurations, all equilibrium structures, inorganic crystals. And the foundation model that came out of it, it's called a foundation model in analogy with the giant models that OpenAI and so on make that are supposed to be good starting points for you to fine-tune, as Alessio was talking about yesterday. The resulting model is stable. That's the first thing that's cool about this. So you can take 80 elements on the periodic table, stick them together in different ways, run MD, and it doesn't blow up. I think that's already surprising and amazing. The fact that it's then also useful. So in this preprint, there are 30 different applications. For example, layering of water at a silica interface. So you take a crystal of silica and you put some water and you have an interface between water and silica and you look at the density profile and it's actually pretty good agreement with, and there's no DFT on here. Many of these things are in surprisingly good agreement with DFT. These are different polymorphs of ice. So without directly fitting on any ice, only fitting on inorganic crystals, the relative ordering of different polymorphs comes out surprisingly well. The other example that I picked out was amorphous. These are things I wasn't involved in. I'll tell you more about the ones I was involved in a minute. Amorphous silicon, amorphous carbon. So looking at different densities and temperatures, things coming out in very good agreement with DFT. I would say unreasonably good agreement with DFT, showing the model is really extrapolating across chemical space. It isn't just reproducing what was put into it. Okay, it was only done with PBE, and there was some plus U in some cases, and there was no explicit long-range interaction, as I mentioned. So the question for me was, can we make this useful for what we're doing, where we've, in the past, spent 2/3 of a PhD building a database and fitting a model? Can we not do that anymore and use these things as a starting point? And I think the broad answer is yes, that everybody should have a go, but be prepared to do some fine-tuning. So of the 40 applications, this is the little one over here that I was involved in. We first took the model and we tried it out on the kinds of things I've been showing you up until now. So looking at dislocations in tungsten as a simple case, looking at lattice constants for tungsten, molybdenum, and niobium. They're not bad. It's a bit soft generally. So these are the C11, C12, C44 elastic constants. It's not, I wouldn't say this was predictive accuracy. I wouldn't use this to do science with straight away, but it works and it does something and it's quick and easy to try. The thing that went a little bit wrong is it had never seen any FCC configurations at all. So everything in the materials project is in its ground state. If you have tungsten, it's in a BCC state. That means it doesn't really know the energy difference between the BCC and the FCC. And you might well need things like that for the reasons that I referenced right at the beginning of the talk, where you have local transformations and you need to be able to describe a range of environments. So that was what we set out to try and fix. I wanted to do it quite cheaply, so we just took a couple of hundred DFT configurations for tungsten. And then I was interested in seeing, if I try and fix the behavior for tungsten, can I also improve the extrapolation to other metals? I did this by only including a tiny, tiny, tiny amount of data for the 2 other metals. So just to set the 0 for the energy, basically. I put in 1 atom on its own and 1 bulk crystal for the other 2 metals, and a couple of hundred configurations covering the sorts of things I would like to do. And then we did this in a couple of different ways. We either fitted the model directly to this very small database, which isn't expected to work very well because it's very small, or we used a fine-tuning approach. And the specific variant of fine-tuning which is used in MACE is called multi-head replay. I'll try and explain a bit how that works. You have your neural network, it predicts energies, and it was trained on a giant database, taken in this case from the materials project. So the original loss function was trying to make that neural network reproduce the energies from the materials project. The naive way to do fine-tuning would be to say, okay, don't reproduce that data anymore, reproduce my small different data instead, and change all the weights of the neural network and come away from where you were going originally and come come and try and fit my data instead. And that leads to a phenomenon called catastrophic forgetting, where the model is maybe very specialized on your data, but has forgotten everything that it knew in general about the periodic table. So the idea of the multi-head scheme is at the end of your neural network, instead of just predicting one energy, you predict two. You have two heads, two readout heads. One of them, the job is to retain the accuracy on the big database. Okay, so the one head is trying to keep reasonably good accuracy on the original database. The other head is trying to make the model also at the same time accurate on the specialized data that you're providing it with. And you have control of the balance between the two. So you have two terms in your loss function, essentially. It's called replay because what you're doing is replaying the original training data, multi-head, because you've got these two heads to balance accuracy between the two things. Okay, so I took literally 200 configurations. I had them already from a previous paper with Cosmin Marinica. 3,000 atomic environments, almost all tungsten. As I said, we just put a tiny bit of the other two guys in to see how it would extrapolate. We did about an hour of fine-tuning, so it wasn't expensive. An A100 for about an hour, starting from the foundation model, so 75 cents, something like that. Not a very expensive thing to do. And I built the data set up bit by bit to see how things improved as I added these different configurations. Okay, so the first thing was to look at elastic properties. That's what I was interested in getting right for my target applications. If you fit the model on its own, of course you can match elastic constants on tungsten using only a few databases. In fact, you can do it a bit better than you can using this multi-head approach. But what's nice is that if you use the multi-head approach, despite not really adding any data on deformed molybdenum or niobium configurations, it does actually get better, or at least not much worse, than the foundation model was for those. Whereas if we fit just to the tungsten data, then of course we get worse on the other guys. So that was quite nice to see. Then I tried to fix this equation of state problem. And actually, this is a work in progress because I didn't do it in the smartest way, but I think it's got good lessons for general audience. I added a little bit of data here in quite a narrow range of volumes. And of course, I fixed it there. But if you look at the multi-head fine-tuning FCC away from where I added data, it flops down again. So buyer beware. And this case, there wasn't particularly good transferability to the other metals. It seems like it's messed up in some way. Sorry, my transition must be wrong. I'll just get rid of that. So in this case, we would really need some information in order to be able to describe the energy difference between the phases and the other metals. That's not something that you can learn, in this case, from one example alone. Okay, last couple of things on this example, and then I'll talk briefly about uncertainties, but we won't go into full detail on that. This is stacking faults, so taking a crystal and sliding half the crystal over itself. Out of the box, the foundation model is really underestimating these stacking fault energies. It's not surprising there aren't many defects in the materials project database, so it hasn't got information on which to do this. But this was quite a good success of the fine-tuning. I put in a few configurations like this, and I improved significantly the description of the stacking faults, which was the thing that I cared about in this configuration. And actually, you could say that the orange multi-head is a little bit better than the blue in this case for the other metals. So there's a little bit of transferability there. Improving it for one metal is at least not making it much worse for the other metal. So this is my sort of summary of this part. If you take the model as it is and you try and apply it for the problem that we wanted, you see this core symmetry isn't quite right. It doesn't quite match the pictures I showed you earlier on. The saddle point actually isn't the right configuration either. But if you squint a bit and only look at the energy barrier, it's not too bad. If you do relax the cores, or so you impose the correct core structure, then actually it's not stable. So we did manage to break the foundation model for the transition state here. But if you fine-tune it, you get the right answer for the right reasons. So you get the right core structure, the right saddle point, and a pretty good barrier quite cheaply. So I think in future I will make more use of these foundation models in my research group. We'll use them as a starting point. We'll add a little bit of our own data rather than building exhaustive data sets. A little postscript on this, since we saw the Alexandria dataset earlier on. This is a moving target, so we've been playing around with this for the last year or so, adding little bits of data carefully, but during that time, 2 or 3 new foundation models came along, one of which combined the materials project dataset that was originally used for the MACE model and a subset of the Alexandria dataset that Savannah told us about. And actually, that works really well out of the box, so I can't publish my paper anymore. Or I have to think how to explain it, how to compare it. So in this case, this is really nice finding that adding in just these randomly generated relaxed crystals, no defects specifically, but enough different crystal structures, was sufficient to capture the stacking fault energy really well in comparison to the original MP0 model, which didn't. The thing is, you would then probably want some other quantity as well, so you would still end up needing to fine-tune, but the new foundation model would be a better starting point than the previous one. And then since the MPA, which has Alexandria, there are another 2 that have come out just in the last few weeks, one which uses 100 million configurations from Facebook, and another one which has quite a high level of theory. So it's really a field which is moving very rapidly and developing all the time. Okay, I wanted to talk... Let me do the electronic structure and then skip the uncertainty. And if people are interested in uncertainty, they can come and talk to me in the lunch break, because I think this is maybe generally interesting for people. So we talked about jumping over effective electronic structure models, but I think it's actually often, if you're interested in predicting thermal conductivity, transport properties, etc., really nice to have something which has electrons in it. And that's where I think there's potentially quite a lot of value. So the way that we have gone about doing this is to take a database not of energies and forces, but of Hamiltonian overlap matrices. So we used the FHI Ames code, which is nice for this setting because it's a local basis code. You could instead do plane wave calculations and project them onto local orbitals with a Vanier code, for example, but we did it directly with a local orbital DFT code. We had a set of structures. This is aluminium. I'll show you some other examples in a minute. And we computed ACE features on those structures. I'm wondering if I've got some equations. I thought I had a slide with equations. No. I will tell you, and then if you're interested, I can tell you the details. Essentially, the on-site blocks in the matrix are just like a potential. You're sitting on an atom and you're interested in the environment, and so you can learn that in the same way that you learn a potential. The off-site blocks are a bit more complicated because they involve 2 atoms and the environment of that bond, essentially. So what we do there is we have a cylindrical environment of the bond rather than the spherical environment that you would have around an atom. But we use a generalization of the ACE that I told you about earlier on. That means, again, it's a linear model, which has lots of advantages. It's really easy and fast to fit. Our loss function is just the difference between the data and the model with some regularization, and we solve it with linear algebra. We don't have to do any neural network stuff. What we get out is effectively a generalized type binding model. It has the crystal field terms included, so it's not just diagonal in the on-site block. It's a full matrix in the on-site block, and it's beyond the 2-center approximation that you get in type binding. And you can see it's reproducing the band structure and the density of states really well. This was done using only 2 DFT configurations. So I just took 2 snapshots from MD. They were quite big structures, because the first version of this code that we wrote only worked at the gamma point, so I made big structures, but now we've actually generalized that. So you get a lot of information, essentially is what I'm trying to say, if you learn from Hamiltonians or from electronic properties compared to just learning from energies, where there's only a few numbers that you get at. If you learn from a matrix, there's loads of data, so just 2 DFT configurations are enough to get the band structure. We have to kind of think about the strengths and weaknesses. So we still have to do the diagonalization. That means it's still going to scale cubically with the number of electrons. We're still solving an eigenvalue problem. But we get to skip the SCF part of the DFT calculation. So if you've done a DFT calculation, you will have seen you're waiting for things to converge and you have to do lots of steps. We jump to the last point. Another way to view this would be as an improved initialization for the SCF. So given a structure, we can predict a pretty good guess for the Hamiltonian or for the density matrix and use that as a starting point that you could then use and do further iterative convergence. Okay, so Valdas is the student in my group working on this. He's actually done some nice work so that we can apply it to something other than aluminium, where we've got many more electrons, by first doing a projection, so we only learn the valence states, not the core states. So he's done this for gold, which has got really quite a lot of electrons. We're interested in light matter interactions in gold. And we do this transformation, and then we only learn this part down here. The transformation is constructed so that the interaction between the core and the valence blocks is as close to zero as we can manage it. Then we just learn that part. And this is, I think, a nice thing to think about. So we're using a linear model here, and that's really nice because it's really easy to fit. You don't need very much data. So as soon as we have just a couple of DFT configurations, we hit an accuracy in the Hamiltonian, which is acceptable. Whereas if you use a nonlinear model, so DeepH is another group doing a similar approach, you have a lot of parameters in that neural network, and you need a lot of data in order to fit all those parameters, essentially. And you may need them. It depends what you want to do. But in this case, we get to higher accuracy with a simpler model. So I guess the message is don't jump straight into the most complicated model possible. Okay, and in this case, the density of states is very good in all three cases. So you don't really need to go to super high accuracy in matrix elements. What you should be thinking about is the accuracy in the quantities that you care about, that you want to compare with, you want to use for spectroscopy, or you want to do something with. Another nice thing about linear models that I was hoping to have a bit more time to tell you about is that you can get uncertainties by not having just one model, but by having a group of models, a committee of models. And you can see then we get a little band up here that shows the model is not completely certain about the spectrum up there, but it's very confident down here, where it is indeed actually quite accurate. Whereas it's hard to do that kind of uncertainty estimation with deep learning models. There are ways to do it. We might hear about some of them later on, but this is relatively straightforward. Okay, I have 5 minutes to tell you some ideas about uncertainty, but not go into the maths. So I said at the beginning, one of the things we focus on at Warwick is trying to train students to think about the uncertainties in their calculations, and those occur at all different scales. Down here, we're choosing an exchange correlation functional, typically for good reasons, but we don't always think about what the effect of that choice is on the output. There are ways to make that a bit more rigorous. So I did some work quite a few years ago where we looked at not just one exchange correlation functional, but an ensemble of them. You might have come across the beef ensemble from Copenhagen group. It was a similar idea to that. I think this is a critical one, so uncertainty in interatomic potentials, but then things go on as you go up. So let me skip a couple of slides. I'll show you this one because it gives you the basic idea and it gets across the main message. So originally back in the gap, we had a way of estimating uncertainties on individual atoms. They arise naturally in a kind of Bayesian perspective on how you do the fitting process, but I think it's really critical to think critically about where those are coming from. So the way that works is you assume that your Bayesian model matches the data, but it's contaminated by some additive Gaussian noise. And the problem is that isn't really a good model for what we're doing when we fit machine learning potential. We have really accurate DFT data. It's not noisy. It's well converged. And actually, our errors are because our model is too simple, not because our data is noisy. So using these Bayesian frameworks doesn't always apply all that well. They assume that you've got additive Gaussian noise, that you have uncertainty in your parameters. You need to learn your parameters. Really, the main problem is misspecification. So I made a nice demo of this, which I will show you very briefly, because I made it and I don't have a way of sharing it with you. So in the Bayesian setting, we've got some data here. I'm holding some of it back for calibration. I'll tell you roughly what that is in a minute. You can see my function here is sin x. I've got data here, haven't got any data here. I've got data here again. If I fit a Bayesian linear model to this, then it looks something like this. You can see where there is data, the green line is matching data fairly well. Where there isn't any data, of course, it's not matching that well. But the Bayesian error estimate, which assumes that all of our uncertainty is coming from noise, is already not very good here, even when I do have noise. If I make my data more like the kind of data we have when we fit machine learning potentials, then we know the coefficients in the model really well. And there's no parametric uncertainty anymore, so there's not very much epistemic uncertainty. There's a little bit here due to not having any data, but that uncertainty is a massive underestimate of the true error compared to the function. So that's the main message I wanted to get across. Don't just use these Bayesian methods exactly without thinking critically. There's another method that we've been using that's called conformal prediction. That works by holding back some of the data, the light blue data, which I've called calibration, and rescaling the error estimates so that they contain a certain fraction of the light blue points, in this case 95%, and in this case that's working reasonably well. So it's got not a slightly more pessimistic uncertainty estimate here, but it is just about covering the true result out here. So that's a method called conformal prediction. It's really easy to implement. The key thing is knowing that it exists and looking it up afterwards. I won't have time to go through the maths of it, but I'm happy to talk with anybody who would like to do so. So I'll skip the maths and I'll just show you as a last thing. Yeah, so what it gives you is a prediction set. And basically we scale up our uncertainties by this factor Q bar, Q hat, and there's a recipe for how to get that factor from using some of your data, holding back some of your data and blowing up your error bars to cover the data that you held back is the basic idea. I'm sorry that I ran out of time a bit. So let's just skip to showing you that it sort of works. So we applied it first to energies, and if we have a simple model, the error estimates are big, but they do cover the data. If we make our model bigger, the error estimates get smaller, they still cover the data. And I think probably we'll show one more thing and then we'll stop. So we could apply it to something more complicated, like a vacancy formation energy or a vacancy migration energy, and then we can, for example, make our model more complicated. This is an ACE model. As we make it more complicated, we get error estimates and they get smaller, but in all cases, they pretty much cover the true DFT data. So I think that's a really useful property for uncertainties to have. Okay, let's put up the summary, which may prompt some more questions. So potentials work reasonably well. I think we need to do UQ. We need to do it not just on energies and forces, but on stuff we care about. Linear models are really good for many things. Consider linear models before diving all in to neural networks. However, if you are using neural networks, fine-tuning is a good thing to know about and can work well. You don't just have to use these approaches at the scale that all the methodology was developed for. You can go up a scale or down a scale, and there are lots of opportunities to do so. And we can start doing fun science with it all. Thank you very much for your attention.